Okay, so now that we understand the idea of translation of a material element and the idea that we can observe it by looking at a path line or a streamline, we also want to think about what happens to a finite piece of material, say a little material element that I've drawn here, and the idea that one piece of material may be undergoing a velocity, but very close to it, the piece of material next to it may be undergoing a slightly different velocity. And so we want to understand the idea that for a finite piece of matter, not only does it move, but it can also be twisted and deformed. And so we've seen in the videos examples of little material elements such as, say, a little patch of bubbles that we might generate here. As it flows into a flow, then it'll get stretched and deformed. And we want to try and understand how we might describe that. And so in very general terms, what we're going to show is that for a deformable continuous medium, that we can decompose its deformation into three terms. We can decompose the motion into three elements. And that would correspond to, first of all, a translation. Second of all, rotation. And if I'm dealing with a solid object, say this marker, then that's really everything. So I can translate a material element. I can also rotate a material element. And that's really everything. I can describe all motions in that way. So for a rigid body motion, this would be everything that we would need. But for a deformable medium, then there's going to be one more component that we're interested in, and that's going to be deformation. And so we're going to have to think about the idea that I can take a material element and I can also stretch it and deform it, and that's going to be broken down itself into two components, into what we might call extensional strains, and shearing strains. And because we're interested in a fluid that's moving at a fixed rate as it comes in through here, rather than a finite amount of strain, we're really interested in the rate at which something is happening. And so these are really going to be, at the end of the day, expressed in terms of rates. And so this will be a translation together with a rotation rate. And so those are what we're going to want to think about. So as a recall, it's something that you can probably remember is what people would call a Taylor series expansion. The idea that if I'm interested in a property at a neighboring place, then I can evaluate it in terms of the function that at some place which I do know. And then also if I take a finite step size dx, then I need to allow for the derivative. And of course, this is an approximation. There will be additional terms which will be of size dx squared and higher. But we're going to neglect those, and we're going to take a very small element, and we're just going to express functions like this. So for example, let's say that I gave you a thermocouple, and I was asked you to measure the temperature at each of these points. So if I put in a thermocouple here, you might measure that the temperature was some value at a point here. And you might be interested in what is the temperature at a neighboring point over here. And then we would express that as the temperature at a position x plus dx would be equal to the temperature at the position x plus, but then I have to allow for the fact that I can take a step in x, I can take a step in y, and I can take a step in z. And so in general, I might express this as the sum of all of the steps that I might write like this, and I would sum these over all possible steps. And so this would be expressed in an index notation. If I express it in Gibbs notation, then this would correspond to, say, the temperature plus the sum of the dot product of a vector step dx dotted into dt by dx, dt by dy, dt by dz. And a simple way of writing that is to write that as the gradient in the temperature. And of course, again, there would be additional terms that we'll neglect, and we'll say that this is a way that we could express the temperature at a neighboring position. So that's relatively easy if we're dealing with a scalar. That could be temperature or pressure or density. But what about if we're interested in the velocity? So we're particularly interested in, say, the velocity at this point. And then I need to understand the idea that, that there's a difference in velocity, and the velocity at this point would be v plus dv will tell me the velocity at our neighboring point. And that's really the main thing that we're going to have to think about. And what we'll show is that we can write this quite generally at the end of the day in the following way, that we can write that the position at a position x plus dx, then we'd like to have an expression for this, and we'll express it in terms of the velocity at the position x, plus, and then the terms that we'll need are going to look like they can be expressed in terms of this quantity. So it looks very similar to what we saw for a scalar like this, but now we have to deal with the idea that we have this gradient of the velocity, and this is a second-rank tensor. And so this tensor, we could say it in words. If we were to express it in words, we'd write it as grad v, or we might say grad v. But notice that there's no unit operation in here. There's no dot, there's no cross or anything like that. So it doesn't mean take a divergence or that. It means that it's actually going to have a series of components where this would be dv1 by dx1. And in the standard notation that we'll use, this would then be dv2 by dx1, dv3 by dx1. This would be dv1 by dx2, and dv1 by dx3. And you can write out all of the other components. And this tensor is going to be the tensor that we're going to have to try and understand in the next couple of minutes. One thing to note straight away that we can think about is we can recognize that the units of this are velocity divided by length. And so every single term in this has units of inverse seconds. And an inverse second is indeed a strain rate or a shearing strain rate. And so all of these terms are to do with this idea that we're going to take a piece of matter, we're going to stretch it, we're going to deform it, and we're going to ask what happens to it as we go on. And so in index form, we would write this as dvj by dxi, ei, ej. And what we're going to do is we're going to try and now think about how these different terms tell us about these different components. And we'll think about it for a general flow like this, and then we'll evaluate it for a very specific example.